Hey everybody, I'd like to welcome Steve Brunton, who's he's a professor at UWashington, but also has this giant YouTube channel under the name Steve, which, as I think we'll find out, you are really into linearizing everything, which is an awesome idea because linear is so much better if you can get away with it. So yeah, welcome, Steve.
Cool, thank you. Thanks for the introduction and for the invitation to be here. And it's nice to, well, I won't say see all of you because I can't see you. It's nice to be here with you all. If you have questions, please interrupt or send them to Greg and he'll interrupt and read them out. I always have about 2 times more material than I can talk through. And so if you find something interesting, we'll just divert the talk to talk about that. So the topic of my seminar today is how we use machine learning for driving scientific discovery. And probably this should be a 2-part title. It's really for scientific discovery and advanced engineering optimization. Those are kind of the 2 big challenges we think about on a daily basis. I want to start by acknowledging many excellent co-authors and collaborators on this work. So on the left, most of the dynamical systems work is with Nathan Kutz at UW. On the right, most of the fluid dynamics work is with Jean-Christophe Loiseau from Paris Tech. And in the bottom row, I'm going to highlight a lot of the work of my excellent postdocs and PhD students along the way. This is just a small slice of the lab that contributed to some of the work I'm going to tell you about today. I realize I don't have a cursor, so I'm going to wave my hands. I think you can see me, and I'm going to say left and right and things like that. And I'm going to talk about scientific discovery at large, but I'm going to use examples from the field of fluid mechanics to highlight what we're talking about. So fluid dynamics is my preferred applied field of interest. Part of the reason I like fluid mechanics is because fluids are central to nearly every trillion-dollar industry. From defense to transportation to energy to healthcare, we live and breathe inside of a working fluid, and so do all of our machines. And fluid flows are notoriously challenging to model, to design based on, and to control. So it is extremely expensive to design a new aircraft or a new artificial heart or a new engine. And what we would like to be able to do is use emerging tools in machine learning to speed up this process, improve our ability to model these systems, and improve our ability to control them. And if we can do this, this could be the key technological enabler for lots of science fiction technologies that we envision for the future. Now, why are fluids hard? So we have in the right, fluid dynamics tasks, things like compression. So when I simulate a fluid, it has millions, if not billions, of degrees of freedom, very, very expensive, high-dimensional supercomputer simulations. We need to reduce the number of variables to key features. We need to be able to get reduced order models, differential equations that are solvable quickly at real time. So Navier-Stokes at full scale cannot be solved on the world's fastest supercomputers in real time. We need to speed this up by millions or billions of times so that we can do real-time design, optimization, and control. Other fluid dynamics tasks in blue, things like smart sensors. If I have a wing, where would I put 5 sensors to maximally inform what's happening over that wing? And that's related to the problems of estimation and control. We eventually want to manipulate the behavior for some desired engineering objectives. Now, at the end of the day, all of these tasks in blue are hard optimization problems. They're fundamentally challenging because the physics is nonlinear and multi-scale in space and time. You can see this on the pictures on the left. And because of the nonlinearity and the multi-scale nature of the physics, that means that my resulting optimization problem is both high-dimensional and non-convex. Now, I like to joke with my colleagues that this is a good thing because this gives us job security. We're going to be having these challenges in blue for at least the next 3 decades because high-dimensional non-convex optimization problems are generically challenging. But these are exactly the kinds of optimization problems we're getting very good at solving in the context of machine learning. When you train a deep neural network, that's a high-dimensional non-convex optimization problem. And so the same way that we use machine learning to build models from data with advanced optimization, we can start building these models of fluid dynamics from data with optimization. We can start solving these high-dimensional non-convex problems with emerging techniques in machine learning. Now, I'll point out, this is not unique to fluids. Everything I'm going to tell you in this talk applies to most fields of complex system science. Again, the challenge is high dimensionality and nonlinearity. We have that in neuroscience. We have that in epidemiology. We have that in climate science. We have that in nearly every complex system. We have high dimensional nonlinear multiscale dynamics. And if that is the case, then everything I'm going to tell you today should apply in those systems as well. Now, why do we think we can apply machine learning to such challenging systems that are beyond the world's supercomputers' ability to simulate? The answer is because patterns exist in your data. So I probably don't need to tell this audience the importance of finding, extracting, and leveraging those patterns as the cornerstone of modern machine learning. But it's also true in fluid dynamics. It's true in neuroscience. It's true in epidemiology, in finance, in climate. Every complex system has low-dimensional patterns of activity that drive that system. And the existence of those patterns is what gives us faith that we can build these data-driven these models from data with optimization, these data-driven models. If you're interested in how this works in the field of fluid mechanics, my colleague Sam Tyra from UCLA wrote a great paper on this that shows how you extract those patterns to enable sparse sensing, reduced order modeling, sensor-based estimation, and fast, efficient control. So a pretty cool paper all about how to do this in fluids, but the same basic technique applies, again, to all of these other complex systems. So this is the starting point for this work, is we're going to leverage these patterns to build data-driven models. And specifically, I want reduced order models. If I have a very complicated fluid flow, I don't just want to learn the original partial differential equation that was too hard for me to solve in the first place. I want to learn a reduced order model, some small minimal differential equation, x dot equals f of x, that captures most of the salient features at a tiny, tiny fraction of the cost. This is what we've been doing in aerospace engineering for the last 5 decades, and it is massively accelerating now because of capabilities in machine learning. So now we're going to have data-driven reduced order models using advanced machine learning-based optimization techniques. And this fits into this notion of a digital twin, which is essentially a surrogate model of some complex system that we want to design and optimize and control. And it's too expensive classically to simulate all of the complexity of an aircraft. So I need surrogate models that are fast, efficient, and flexible, and still capture enough of the physics to be useful when we actually design and optimize these systems. So this is currently in the kind of central discussions of every major aerospace company in the world today. Every company that builds something is talking about how to do it faster and better with data-driven surrogate models, aka the digital twin. And so what I'm going to tell you today really fits into this picture eventually. So I do a ton of work with Boeing and other companies, helping them roadmap how to get machine learning into their design, optimization, and control pipeline by building these surrogate models. And again, we want them to be hybrid physics-based and machine learning. We don't want to forget physics, and we also don't want to stop using our data. We want a hierarchy of models from low fidelity to high fidelity. And this last bullet point, I say this to people at companies, aerospace companies, and they glaze over. But I think for the for the Google crowd, you should appreciate the real benefit here is if my digital twin is developed in a machine learning environment, then it will have end-to-end adjoint-free optimization. I can do optimization from point to point without actually computing an adjoint by hand. That's huge. That saves, hundreds of human hours over the course of a large project.
So let me actually poke on this. You
Yes.
mean there's a neural gradient as opposed to a manually derived gradient?
That's what I mean. And it doesn't have to be a neural network, but yes, you can think about it like, yes, using essentially the same technology as auto differentiation and backdrop, we can do this sensitivity analysis that currently, when I said hundreds of hours, I meant hundreds of years. Literally, a human, if I want to build one of these adjoint models, it takes like at least 2 human years for a complex fluid. And you've got dozens of people doing this, for dozens of systems at a company like Boeing. So this is literally hundreds of human years if you can remove that adjoint calculation from the process.
Right. And Federico, you have a question?
Hi. Can you hear me?
Yes, I can hear you.
Oh, perfect. First of all, like, big fan of your YouTube channel and your textbook. Thanks for coming to give a talk.
Thank you.
2 questions here. One is sort of the adjoint-free optimization. If that's the advantage, why not just rewrite the PDE simulator in like a modern auto-diff framework, and then you get to do the same? You get the derivatives for free.
Yeah, that's a really good question. So a few things. People have done that, and actually some of the best work is happening at Google and Google X, actually. So like you guys are doing this right now. So like JAX CFD and JAX fluids are, like people's attempt to do that. Until very recently, these were limited to very, very simple 2-dimensional systems. And scaling, if you want to do a real production level code, like a heavy duty, I'm going to design an aircraft with this code, or an artificial heart, those are a lot more complicated than your off the shelf ANSYS, OpenFOAM kind of general purpose, JAX kind of fluid solver. They're a lot more specialized, a lot more fine-tuned, and there's only a few groups in the world who have that computational capability. Those codes are very hard to port into an auto-diff framework. And there have been pretty bad scaling issues when you go to extreme scale fluids problems. And I don't know all of the technical details. I'm sure it's related to conditioning and stiffness and all of the numerical issues that you have generally. But I do know my friends have told me that going from like 2D to 3D has been incredibly challenging. Going from low order to high order has been incredibly challenging. So there are researchers doing that, and Google X has some of the best teams doing this, for example, for their climate simulations. But it's difficult. And I want to do it on these reduced order, these baby models. I don't want the full CFD because I'm not trying to take care of every minor vortex in the flow. I want to control the patterns. So I want to do this on the reduced order model. Infinitely easier to build a differentiable model, with 5 states as opposed to 5 billion states. Great question. Brilliant question.
Yeah, and the other question was sort of about the digital twin. Like, I've worked in this area. And one of the, I don't know if this is something that you're going to be talking about, but one of the challenges is that it's very easy to train a digital twin, which is a high fidelity simulator in the regime where it's trained on. But then you'd like to use it to do control. And if you linearize it and so forth, and if it were a simple system, you've got like nice theorems that tell you in which regime the thing it's valid in. The moment you train a surrogate model, which is instead a neural network, the validity outside of the training domain is exceptionally difficult to establish.
So that is literally the entire topic of my talk from now on.
Okay, so great.
You're absolutely right. Okay, I'm going to jump into it. I'm going to address that question. Great point. So that is essentially the main issue, is that our surrogate models, these guys here, tend to work really well where you train them. But the minute you turn on control, or you try to change your shape, or you do the design optimization control that you want to do, you push yourself out of the regime of your training data, and your model fails to generalize. That's the core problem with neural network-based designs and most machine learning-based designs and most surrogate models in general. So I'm going to tell you of how we start to address this issue. And I want to point out, this is not a silver bullet. This is not a panacea. We have not solved the problem. This is our attempt to get towards solving that. Lots of people are working on this. So based on your question, I probably don't need to tell you that we desperately need machine learning models that are more interpretable and more generalizable for these kinds of engineering-based designs. And again, I work a ton with companies like Boeing, Blue Origin, and if you are going to design a safety critical aerospace system, you need your machine learning models to be interpretable and generalizable. Now, depending on which audience I talk to, I get in a fight every time I try to define these terms. I'm not going to define these. I'm just going to tell you what I mean by interpretable and generalizable with an analogy. My favorite example of an interpretable model, Newton's second law. Clearly interpretable. It has three terms: force, mass, and acceleration. They have units. You can write this down on a napkin and go to a coffee shop with your friends and discuss what these terms mean. It's highly interpretable to humans. And it's generalizable in the sense that you can learn F equals ma from observing an apple falling on Earth, and this model still is valid when we land humans on the moon. That is the ultimate generalizable model. And so you can train a neural network on videos of apples falling. You probably need, 1,000 videos of 1,000 apples falling, and I could make a neural network that would fool every single one of us. We would not be able to tell truth from fiction, but that neural network will be useless when we land humans on Mars. So what we want is something much more like F equals ma and less like a neural network. If we could, we would want the physics of the system, because physics is what generalizes. And so this is an idea for 2,000 years. This has been the gold standard of how we build models that are physical. From Aristotle to Einstein, 2,000 years. The models that are physical, that capture the physics, the generalizable nature of the world, are the models that are as simple as possible to describe the data, but can be made no simpler. Okay, I'm going to say that again. Physics, a good working definition of physics, are models that generalize. And to find those physical models for the last 2,000 years, the way we've done it is through this principle of parsimony or simplicity. We want the simplest model that describes the data and no simpler. That's F equals ma. That's E equals mc squared. That's Pareto optimality and Occam's razor. This was all the way back in Aristotle. He knew that simplicity and beauty was how you found generalizable physics. So that's the principle we want in the modern machine learning era. We need our machine learning models, instead of being as complicated as possible to describe the data, we would like them to be as simple as possible to describe the data and no simpler. And I'll point out, this is not trying to say that we shouldn't use neural networks. Clearly, we have these immensely powerful technologies we should be using, but we should not be forgetting 2,000 years of history of what has allowed us to generalize in the past. And that's finding the simplest models that describe the data and no simpler. So mathematically, today, we have two tools at our disposal to find these simplest models. We have low dimensionality and sparsity. Low dimensionality means if I have complex high dimensional data like a fluid, I want to find those fewest patterns that describe that data. That means low dimensional. I want a vector that's low dimensional to describe that complex high dimensional system. I can promote low dimensionality with the L2 norm. And then I want sparsity. If I'm going to write down a differential equation, x naught equals f of x, to describe those low dimensional patterns and how they evolve in time, I want my differential equation to be as sparse as possible. I want the fewest terms in the equation. I don't have f equals ma plus nb plus ... I just have the fewest terms needed to describe that system. That can be quantified with the L1 norm. So there are mathematical norms at our disposal to promote parsimony in machine learning systems. And if we fast forward to the modern computational era, this starts to look a lot like the Lorentz 1963 model for chaotic thermal convection in the Earth's atmosphere. So this model is the simplest model to describe the chaotic thermal Rayleigh-Benard convection that drives our chaotic Earth's weather patterns. And if you look at this Lorentz 1963 model, it has the hallmark features we're looking for. It is low dimensional. This differential equation only has three variables, x, y, and z. This fluid simulation has 1,000,000 degrees of freedom. The Lorentz system has 3 degrees of freedom. It's low dimensional. X, y, and z are the amplitudes of 3 spatial modes you would add up to approximate this flow field. Those modes were proposed by Saltzman at Yale a year earlier. So it's low dimensional, 3 variables. And if you look at the differential equation on the right, out of all of the possible things you could write down to describe this behavior, this differential equation is very sparse. It's very simple. It has 7 terms, 5 of them are linear. So this is a model that is as simple as possible. You can't make it simpler and still describe this phenomenon. So this adheres to that principle of parsimony, of generalizability. And the Lorentz 1963 model does actually generalize beautifully to chaotic regimes, to periodic regimes, to many, many phenomena well beyond where it was trained. So it has that generalization capability as well. So what I'm going to tell you about now is how we use very, very simple data-driven optimization techniques, you could call this machine learning if you like, to learn models that are more like Lorentz 1963 and less like a deep neural network. Okay, so I'm going to tell you about the sparse identification of nonlinear dynamics, the SINDy algorithm. This is something we developed just under 10 years ago. And I'm going to show you how it works on the Lorentz 1963 problem. So this is a warm-up. This is just to show you how it works, and then we'll apply it to systems that are much more complicated. We are going to pretend that we have data from this system. We can measure x, y, and z in time, and we can approximate the derivatives x dot, y dot, and z dot. We will relax that assumption later, but for now it helps make this easier to understand. But we don't know the equations that generated the data. We only have data in these colorful columns, x, y, and z, x dot, y dot, z dot. Now we have to ask ourselves the question. Remember this Einstein quote, we want the simplest model to describe the data and no simpler. What's the simplest model you can think of? You can unmute yourselves, you can jump in, or you can just think about it. Simplest model you can think of? Most people say linear. Even simpler would be x dot equals 0, y dot equals 0, z dot equals 0. That is the simplest model, but it's too simple. It doesn't describe the data. So let's try the simplest model that might describe the data, which would in fact be linear. This is what the dynamic mode decomposition does, is it uses linear regression to find a best fit A matrix, a best fit little 3x3 linear system that best describes x dot, y dot, and z dot. It's a very simple system. But this linear DMD matrix is too simple. It has a single fixed point at the origin, but our Lorentz system has 3 fixed points and infinitely many unstable periodic orbits and a chaotic strange attractor. So this linear system doesn't satisfy that Einstein quote. It's too simple. It doesn't describe the data. So what we do is we augment the right-hand side with more terms that could possibly describe the dynamics. In this case, polynomials up to 5th order. Not just x, y, and z, but x squared, x, y squared, all the way up to z to the 5th. You don't have to use polynomials. You could use sines and cosines, Bessel's function. You could use tailored functions. You could use neural network functions, anything you like. Polynomials work beautifully for fluid systems for some reasons I'll tell you about later. And importantly, I can compute each of these gray columns from the data I have. If I have x, y, and z, I can compute x squared and xy and xz, okay? And so now we're trying to find the simplest model in this class of models. This is a family of models. I'm trying to find the simplest model that describes x dot, y dot, and z dot. And simplest here means sparse. I want the fewest columns of theta that add up to equal x dot. I want the fewest columns of theta that add up to equal y dot. And I want the fewest columns that add up to z dot. 20 years ago, this was an NP-hard, brute force, combinatorially hard problem. This didn't scale with Moore's law to find sparse combinations of a library to equal some vector. Now, this is one of the big advances of machine learning is actually not the neural networks, but the optimization algorithms we use to train these neural networks. Our optimization algorithms have gotten so much better. We can solve these sparse optimization problems using relaxed formulations that do scale with Moore's law and do converge to the true answers with very high probability. And you'll notice the terms that are highlighted in blue, in red, in green are exactly the terms in the original differential equation that generated the data. So in this procedure, by finding the simplest model that describes the data, the sparsest model, we actually uncover the nonlinear differential equation that generated that data. We uncover the true model from the data. This was kind of a holy grail problem when I was in grad school. Now this is a couple of lines of Python code. So we have a really nice open source software, SINDy. This has been maintained by groups all over the world, including my own group. If you have time series data, you can learn differential equations now from that data. And of course, what we have done here is rediscover something we already knew. Very soon we'll go on to discover new differential equations from data where we did not know the answer. So the next step that's kind of cool, our PhD student at the time, Sam Rudy, realized you could extend this to learn partial differential equations in the same way. So if you have spatial temporal data like this fluid flow, you can build a library of partial derivatives and products of those partial derivatives. And when you apply the same sparse regression procedure, you can learn the identified dynamics. You find that you learn the coordinate form of the Navier-Stokes equations. Okay, this is where I polarize my audience. So half of the time people are like, this is so cool. Like the Navier-Stokes equations took humans a really long time to learn. It's a very complicated PDE. That's super cool that this algorithm can learn it purely from measurement data. The other half say, well, this isn't anything special. Clearly, you already knew the Navier-Stokes equation to begin with. You know, it's not that surprising that you could relearn them from data that was simulated using the Navier-Stokes equation. And I think both are true. These are both valid perspectives. But what I want to point out, and I think this is essential for everybody to hear, I say this every single talk I give now, if you are going to develop a new machine learning algorithm, if you're going to build a new algorithm to do something, please, please, please test it on a system where you know the answer. Very often, far too often, I see researchers develop a very complicated new machinery, and then they apply it to the hardest problem they can find: galactic formation, protein folding, cancer research. Apply it to a system where you know the answer first and see if it works. See if it gives you the results you expect. See how it breaks and diagnose it there. In the time since this rediscovery, this is a rediscovery, Sam Rudy's paper, we took 10 canonical textbook PDEs and rediscovered them from data. Since this paper, researchers in my group and groups across the world have used this algorithm to discover new partial differential equations that no human has ever written down before. Real scientific discovery. Systems like plasma physics. We know that the magnetohydrodynamics equations are a mediocre approximation at best to real plasmas. And researchers at UCLA and SINDy have used this algorithm to learn new partial differential equation closures to describe plasma physics better. People have used this to develop new turbulence closure models, both Reynolds average Navier-Stokes and large eddy simulations. New closure models that have never been written down before can be learned using this procedure. Similarly, granular material, particle flows and granular material, you can learn partial differential equations for those systems. Neuroscience, my wife Bing and I work on learning PDEs from the brain, from brain dynamics, surface waves, using this algorithm. That's what we call scientific discovery because we've gone beyond the kind of rediscovery phase.
So this is actually perfectly into like the big question, this philosophy of science question. Yes. I get how all the stuff is useful for optimization, running things quickly, because obviously these equations can be done very quickly. But what the side effect of coming up with a Navier-Stokes or I'm thinking like material motion, like the basic model of like a rope moving up is this basic idea I have a bunch of beads on a string. They can move only up and down, and my velocity depends on the distance between me and my neighbor. And that's a thought, and I can use that concept to figure out when this model is going to work, when this model is not going to work, try to think about where atomistic connections are going to be made. And Navier-Stokes, it's more like, it's a curl and like the regional like vorticity kind of intuition. Do you get these intuitions when you rederive these things? I mean, transferable, applicable to related domains intuitions when you derive it via machine?
Yeah, that's a great question. The short answer is yes, sometimes, but it doesn't come for free. So maybe I will, let's see. Yeah, so I'm going to use this library as an example. So how do I want to say this? Okay, I'm going to take a big step back. What is physics? So I gave you one definition of physics. It's models that generalize, and typically that means simple models, the simplest models to describe the data. But we have other notions of physics too. The biggest notion of physics beyond that is symmetries and invariances. We know that mass is conserved, momentum is conserved, and energy is conserved. We know that every conserved quantity or invariance gives rise to a symmetry and vice versa. There's this deep relationship, Noether's theorem, that connects symmetries and invariances. These library regression procedures, there's this dual problem of enforcing symmetries that you know and learning symmetries that you don't. This is one of the deepest problems in physics, and it's one of the most interesting problems in machine learning. If I have partial knowledge of my physics, I know that energy is conserved, and I know that that gives rise to a symmetry. I can enforce that in this regression procedure. These coefficients C, instead of doing a sparse least squares, I can do a constrained sparse least squares. I can add constraints in to enforce given symmetries by construction and by optimization. Similarly, I can use the dual problem to learn which symmetries cause my error to crash and for me to actually get the simplest model with really, really low error. And once you find the right symmetry group, you definitely know it because your error collapses and you have this like a much, much simpler model. So we can discover symmetries we didn't know, that generalizes, and we can enforce symmetries we know to help our system generalize much, much better than it would have otherwise.
That actually makes sense, because actually, and how would you describe a symmetry? Because the literal form of the equations looks kind of confusing.
Let me see if I have this slide. Sometimes I talk about this, sometimes I don't.
Yeah, I mean, I'm thinking standard physics.
I don't know if you can see this equation here.
Yeah.
But there is this skew symmetry in these quadratic terms. Here I have an AXZ and an AYZ in the X and Y equations. And in the Z equations, I have like a minus X squared and a minus Y squared. There are these basic known kind of symmetries that you would have in, sorry, I'm jumping the gun. Let me give you the short version of this answer.
Mm-hmm.
Symmetries is a huge, huge topic.
Mm-hmm.
I can have continuous symmetries. I can have rotational invariance, translational invariance, all of these different symmetries and invariances. Those are described by Lie groups, by differentiable manifold groups, that the dynamics, the system should be invariant with respect to or equivariant with respect to. And in the context of machine learning, we know how to build equivariant neural networks so that the input-output relationship is invariant to certain Lie group symmetry transformations of the data. In the case of these fluid flows, those continuous symmetries on space and time project down to discrete point symmetries on these ordinary differential equations. It's a complicated field. This was studied a lot in the 1980s and 90s and 2000s before heavy computation. We know that these continuous symmetries that we think of, like translation invariance and rotation invariance, those also have ramifications in terms of our reduced order models, in terms of symmetries on the actual terms in the differential equation. So my fluid flow equations have skew symmetric quadratic nonlinearities. Energy conservation in a fluid means that my quadratic terms have to have a skew symmetry. And that skew symmetry can be encoded and enforced in the SINDy procedure.
So this is the other way around. You know which symmetries already exist.
I know what symmetry, but it's a very general symmetry. It's energy is conserved, and that means any nonlinear model I have has to have the skew symmetry. So that's still an infinite class of models, but they're constrained to be skew symmetric. That will enforce energy conservation.
So cool. So now I want to find a brain symmetry, and like I can see like sleep is one hypothesis that we accumulate enough toxins, we have to sleep, otherwise we die, and sleep does that. That's kind of feels like a symmetry, or does a symmetry can be derived from there, but God knows. How can you derive such symmetries for a nasty, nasty system?
Yeah, so you have just keyed on to one of the most important research directions in my lab. I think it's the most interesting question. Like there might be 4 or 5 driving questions we ask. This is one of them. It is, what about approximate symmetries in there? Okay, I'm going to restate exactly what you said. When I'm driving down the freeway, there is clearly a symmetry or an invariance. Sometimes you space out on the highway.
Mm-hmm.
But you have this feeling that if something interesting happened, if something was dangerous or interesting, you would be there and you'd be able to respond. Because your brain is factoring out that invariance. It knows the flow of traffic. And if anything violated that symmetry, if anything broke that invariance, you'd be on it and you put all of your attention into understanding and controlling that. Because all systems have these approximate invariances. Financial systems do, epidemiological systems do, brain systems do, traffic systems do. All of these systems probably have a PDE and they probably have invariances, but they're not exact invariances. They're not perfect, machine precision invariances. They're fuzzy. So how do we learn fuzzy symmetries and fuzzy invariance? That's a huge question my lab answers. I'm going to try to share a different slide because I actually just gave this talk in Croatia last week. To a bunch of mathematicians. So I'm going to give a slightly different talk for 5 minutes because your question is really good. So how do we actually build physics into machine learning and learn physics with machine learning? So it's a dual problem. One of them is to discover physics we didn't know. That's what you're saying. If there is an invariance or a symmetry in the brain, can I discover it? The dual to that is if I know some physics, some symmetry, some invariance, how do I enforce it in my machine learning and make it much, much more generalizable? And so, the idea here would be I could build an autoencoder to learn the motion of a pendulum. But what I really want is I want to learn the actual dynamics that generalize. I want to learn the physics. This will generalize. It'll generalize for larger angles than I measured. That's not true with a neural network. So the way I think about this is that there are 5 basic stages to machine learning. This is an approximation. We don't all agree on this, but it's fine. You decide on a problem. You curate your data to train the model. You design an architecture or a family of functions to approximate that input-output data. These are parameterized families of functions. You craft a loss function to tell you if you did a good job or not. And you employ some optimization to tune the parameters of your architecture to minimize your loss function averaged over your data. This is approximately the procedure. Clearly, you always have to really go back and forth between these steps. It's never linear like this. They're all coupled, but these are the basic steps. And every single step here gives you an opportunity to embed physics or to learn physics. So I actually always joke when I'm giving my talks that bullet 2, this is like the Google approach. Right, Google has infinite data. You guys have had so much data of images that you can learn symmetries, camera transformations, because you've seen every white Toyota pickup truck from every possible imaginable camera rotation and translation and scaling. So by having infinite data, you can essentially learn physics. But in scientific ML, we don't have that luxury. We have to be clever with designing our architecture, designing a good loss function, and employing an optimization algorithm to embed that physics or to learn that physics. So I usually work in bullets 3 and 5. PINs, the physics-informed neural networks, are usually in bullet 4. But the idea here is that physics, this idea of invariance and equivariance, you can both enforce this and you can learn this. And Sam Otto, who was a postdoc working with us, showed that this is a dual problem. So this is like a 50-page monster paper that Sam wrote, basically showing that there are these dual problems of enforcing and uncovering symmetries in physical systems. And this applies to SINDy, this applies to neural networks, this applies to any data-driven optimization architecture. You have some large superclass of Lie group symmetries that could be true. So if I have rotations and translations, then I could have some superset of general linear group of translations and rotations and, symmetries. And I'm trying to find the largest symmetry group that my data is equivariant with respect to. So that would be the basic idea here, is that you can learn symmetry groups or you can enforce them. If you know some symmetry group, you can do constrained optimization and force yourself to be on that asymmetry group. Okay, sorry, that was a pretty big tangent. But
as a summary, find the biggest symmetry that my data is equivariant to is a very solid summary.
Yeah, and that doesn't have to be a machine precision statement. Yeah. This is based on finding a large null space in a larger space. And if you're trying to find a null space, you get to determine where you consider something to be rank 0, you know, like, you know where the noise floor is in your data, and you get to determine what is below that noise floor and counts as a subspace or a rank 0 subspace. So you get to determine, you know, what is and is not a null space and where to draw that line.
Cool. One more question before I take you, Federico. A lot of work in causal discovery is based on having independent systems that when one side moves, the other one side does not seem to move, which is just a causal edge. This seems like an important technique for starting to discover the structure of these symmetries, because we're talking about groups, and a giant group is going to be made up of a lot of little groups composed together. It means like useful.
Yeah, no, that's a really good observation. And we haven't looked at this a lot. My colleague Nathan Kutz has definitely looked at causal systems a little bit more than I have. I'm trying to see if I can go to SINDy somewhere. If you look at the Lorentz systems, though, any system that truly has feedback, the notion of causality breaks down. You can't say that X causes Y or Y causes Z or Z causes X. This is a causal unit. And it's not really, so yes, causality is a real thing, and there are cases where you can tease it out with data-driven methods. Sometimes you have causal blocks with feedback loops, and that is where it gets messy. People have used SINDy to tease out causal networks, though.
Right, it makes sense.
Great question. Federico, do you have a question as well?
Yeah, one was sort of at the initial question that I asked about like models that generalize. Like, I really like the SINDy line of work, like the follow-ups of neural networks and so on. But I think to make a simple example, let's say that you're trying to identify a sparse system on a pendulum, and you gather data in the linear regime because that's the data you have available. If you then train a sparse system, it's never going to generalize to the nonlinear behavior, because that's sort of where the data you've gathered it is. So how do you get, like, have you found anything, like, have you started doing work with like active learning to probe areas where ensembles of models start to fail? Or absolutely. Like, how do you think about this situation? The other thing was sort of a comment on like equivariance and invariance and so on. I'm not sure if you read the AlphaFold 3 paper, but it's kind of interesting because in AlphaFold 2, if you remember, they put in a huge amount of work into building equivariance into the network to respect all of that. There's a paragraph in AlphaFold 3, which is kind of like a dagger to the heart, which basically says, we found that training for longer, we can just strip out all the equivariance and invariance bit, and the model actually works better. So, and this is in the case of protein folding, where you don't have infinite data. So even in that case, they basically, there's a fair bit, but there's not infinite. So I was just kind of curious.
That's a really good point. And I mean, this is a perennial debate about whether or not tailored knowledge is good or bad. I mean, this is the bitter lesson, right? This is Sutton's bitter lesson on steroids now. I would think that the biggest argument is that in the third iteration, they had much, much better machinery and a better knowledge of how to use their training data and their prior knowledge with that machinery. And I bet in the future, incorporating known physics will still improve that procedure. I think those are two different papers. Like, you can't expect one major advance to solve both of those problems. My feeling is that you will still get a benefit from incorporating known physics in generalizability. That's a pretty different realm of how much data is available still than what I'm talking about in fields like fluids and climate, though. You're talking about active learning, though. Yes, absolutely. I'll just give you a couple of teasers. I mean, if you book a system in the linear regime and you only collect linear data, it will learn a linear system. But if you start giving it a little bit larger amplitude data, it'll learn the cubic approximation. Then it'll learn the fifth order. But if you give it sines and cosines, very quickly it will learn that sines and cosines are actually better, because there is a small discrepancy at seventh order. And it will learn that sine and cosine is the simplest model. It's better than a 3-term Taylor series approximation. So you will learn, even from relatively small amplitude pendulum data, that the thing can go around in a circle. That is a generalization that you can learn. But your question, maybe I'll just make this big.
But I think, sorry, to comment on that, like,
your question, if I'm going to restate a question that I can answer. What if I have multiple models that could equally well describe my data in this library? Let's say I have an oscillator. And that oscillator could be a linear oscillator, it could be a cubic oscillator, it could be a fifth order. I can write down a dozen equations from this library that would give me oscillations. And that means that this matrix theta is singular or nearly singular. It's ill-conditioned. It has a terribly large condition number. And if I have a matrix theta that has a large condition number, and I can compute this condition number when I'm doing my regression, every time I do my least squares, I compute the condition number. That tells me what are my degenerate subspaces and what are my candidate models that I can't refute. That allows me to build new experiments to maximally improve my condition number. This is a line of work in our lab, is exactly that, doing active learning to add rows that maximally improve the condition number as fast as possible. So we absolutely do that. Urban Fazell started doing that in his paper on ensemble SINDy, and that's been a huge, huge benefit to have this active learning component.
Okay, no, great. I think that specifically to your comment about like adding signs and that they generalize better, I think the challenge there is, of course, that like if you have a simulator and you can generate infinite precision data, or then this is relatively easy. Or you perfectly set the trade-off, because you've got the trade-off between fit to data and regularization, and a linear model is still simpler. So a linear model might be preferred even if the other model is better if you regularize too much, right? And yeah, so then
exactly, that's a function of how noisy your data is, how aggressively you regularize, and there is something I didn't mention. There is a sparsity parameter. You get to pick that regularization. You get a family of models, some of which are more complex and more accurate, some of which are less complex and less accurate, and you get to pick that Pareto optimal, that kind of Einstein point, if you like.
Yes.
And for low noise systems, that's kind of obvious. For high noise systems, it's a little less obvious. But ensembling and weak interval forms usually crush the noise down by at least an order of magnitude and give us that crisp edge for most problems.
Have you looked into, I think the work, it's by Mark Transtam from Utah, where he instead tackles it from like a model reduction point of view. I think he was part of the Sethna group and all the work connected to like sloppiness and so on.
I am not familiar, at least off the top of my head, with that.
I'll email you later. I think you might find it interesting.
Yeah, thank you.
Yeah.
So actually, since we've hijacked your talk and actually are interviewing you now as opposed to your slides, let me try being big picture. So if we're thinking about like complex hydrodynamics, where we barely know how fusion, like the nastier, the nuclear force, and Magellan hydrodynamics, or vehicular traffic in a city, like coming up with those equations. There, I think we're actually going to the real problem. Not I have a data set, what's the best model for it? I want to figure out how this damn system works. And there, the scientific process is more like, let's say, vehicular traffic. It's easier to visualize. I see a bunch of cars going in no traffic, maybe a couple samples in some traffic. We may see a traffic wave once. And I see somebody trying to parallel park badly. And these diverse phenomena, which have maybe their own models. And there, the task is to heterogeneously combine all the available evidence. Like, I know how a string works. I see the pendulum moving. And from those two different lines of experimental basis, I have to figure out how a pendulum would work when you combine them. How can we use these techniques to solve these really challenges for which we have no good science today?
So I'm a part of a startup company called Collimator. And in Collimator, we are integrating lots of the technologies you're describing. So we have SINDy, we have autoencoders to find good coordinate systems, and we also have kind of custom LLMs that allow, for example, to look at the board behind me and say, like, what's the type of physics we're talking about? Like, what's the category? What are we looking at here? Oh, it's a pendulum, it's a spring mass tamper system, or oh, it's a flow. Like, how do we do flows traditionally? Well, if I do my correlations in the literature, I could probably model this with a PDE that's one-dimensional and has some viscosity, and I could you can start building these models. Okay, maybe I should have a shock wave and a rarefaction wave, and so then you can start guiding SINDy with kind of human level expert knowledge of what you're looking at. Like, that's not production level, but that's definitely where I see this going, is you have a family of models like normal forms, And you start guiding, if I ever see a system that looks like Lorentz that has this chaotic switching, I know that there's a coordinate transformation that takes me to Lorentz. So I know that I need to build an autoencoder network to find that coordinate transformation. And that's the kind of thing that can be automated, I think.
Okay. And to what extent, I mean, this makes me think of simulations, generic regular simulations, as summaries of a century of body of knowledge from a given area. You don't get the raw data, you get their summary. To what extent can they be used as a foundation, as a representation of learned knowledge that's not fully available to you?
Yeah, that's a really, really good question. I mean, I'm not sure. So this is a really interesting philosophical question, and I think this is something we talked about a lot in the community before LLMs. And so I think the conversation probably changes a little bit now, and we haven't had these conversations as recently. But if you think about it, and I want to solve all of fluid flows. I want a machine learning model that can just tell me how a fluid behaves. To some level, we already have this. It's called the Navier-Stokes equation. That is the best model. Like, it's a hell of a model. It's really compact. Very few bits. There's computational ways of unrolling it. Like, it's an extremely, extremely concise summary of a huge class of physics. So there is this question, like, if I apply machine learning to just volumes and volumes of simulations of Navier-Stokes, what do I want to learn? What is reasonable for me to learn? Like, I can't learn a model that's probably better than Navier-Stokes in terms of simplicity. I probably can't learn a model that's better than some, super highly optimized finite volume or finite element in terms of speed for a particular problem. So, you have to start asking what you actually want to do here. What's the representation that's useful for you? And I mean, our colleagues at Google have asked that question and, for example, improved finite element and finite volume simulations, because there is room for improvement with learned stencils and learned test functions and things like that. That doesn't really answer your question, I think.
Not quite, but let me ask a less than same question, a more answerable question. What you're describing sounds to me like, my background is Department of Energy. So they had, you have a regular grid where you solve fluid dynamics and it takes forever. So you have adaptive mesh where you say, well, there's more stuff happening, more dynamics happening here. I'll have a finer mesh, finer time resolution. Somewhere else I'll have something else. But what we're talking about here is, this spot I have a wing that's kind of wobbling. This part I have a vortex. This part I have a bird, and they're all doing different things. Why don't I have different models just executing different parts of the space, and it can all be SINDy, but optimized for different phenomena?
Okay, so you're asking the most excellent questions. I'm very selfish. I think they're excellent because these are the questions we ask.
Yeah.
This is a major, major research direction in my lab. This is another one of the big ones, is what we call finding regions of dominant balance. So dominant balance is something we used to do before supercomputers, where you would take a super complicated fluid like this, and you would have to make simplifications, like a human expert would make simplifications so that you could solve this with pencil and paper. So this is full 3D Navier-Stokes. You can, break this down into Reynolds average so that it's a PDE with 6 terms, still quite complicated. And what you can do is you can actually compute every single term in this equation everywhere in space. And what dominant balance says is that ideally we would have some regions of space where only a couple terms are large and active, and other terms are approximately 0. So you can see with your eye, there are some regions where some subset of the physics is active and everything else is 0. And so what you do is you take this representation where now every point in space has 6 numbers, one for each term in the equation, and you can take all of those points in space and you can scatter plot them in your 6-dimensional equation space. These are some slices of equation space. And just with your naked eye, you can see that there are subspaces where the data lives. If I cluster those subspaces and I learn the sparsest coordinate model in those subspaces, you start learning that there are 5 clusters, and each of those clusters has different terms in the equations. Now, each of those points was a spatial point, so you can replot them in space. And now we have a picture of our fluid flow boundary layer color-coded by what physics is active. So for example, we learn now about the viscous sublayer, the inertial sublayer, the transitional region, purely from measurement data of which terms are active where in space. So that's kind of what you're describing, is you can start learning that, oh, flutter over here, that's a subset of the physics. The corner flow on the wing, that's a different subset of the physics. It's in the data because there's different physics that's active in those regions. We've applied this to lots of systems. We've applied this to fluid flows, laser flows, Gulf of Mexico, climate flows, bursting neurons, combustion waves. And one of the things that it begs the question is, if you notice the red and the blue region here, they have an interface and they have one term in common and one term that's different. So as I go from red to blue, I have to kill the diffusion term and I have to pick up a convection term. That means there's a non-dimensional number that mediates that transition. So the last thing we did here is actually use this idea of non-dimensional scalings to learn in the data what are the non-dimensional parameters that mediate the transitions between these large changes in behavior or large changes in physics. So this is like the Buckingham Pi theorem, but baked into a neural network. That's probably, I realize I'm basically at the hour. These have been excellent questions.
But maybe what you described makes perfect sense. I've seen what you're describing in cell analysis paper where they cluster population by their different dynamics to figure out what the dominant ones. This sounds like a very general pattern. Yep. So maybe in the last few minutes, maybe if you can summarize kind of your takeaway messages, because there's, like I said, you have a ton of slides, but you do have these big ideas that are transferable to all of us.
Yeah, so the big ideas are pretty simple. The big ideas, as I see them, are that I'm not saying we shouldn't use modern machine learning tools. We absolutely should. They're amazing. They solve big, big problems. But I think we sometimes run into problems by pretending that those are the only methods. Young researchers often only work with the biggest, fanciest, newest algorithms. And sometimes there's a lot of benefit by finding the simplest model that describes the data. That gives you a better chance of generalizing and having interpretability in small data sets where you have some partial knowledge of the physics. These can be very well combined with powerful tools in neural networks and machine learning. For example, in this Buckingham Pi network, or using autoencoders to find good coordinates, things like that. But fundamentally, patterns exist in your data. Those patterns mean that there are simpler representations, and learning and uncovering those simpler representations often gives us an edge in generalization. I guess that's some main takeaway, at least.
Awesome. Well, yeah, thank you very much. It was extremely valuable.
Yeah, thanks for the great questions and for the invitation. This was a lot of fun.
Absolutely. Have a great rest of your day.
Cool. Take care, everyone.
Bye.
Bye.